Okay, I think we can get started. I will be recording the lectures from now on and posting them online, so you have some additional reference on top of the notes. So I'll start by reviewing some material from the last lecture. Last lecture, we introduced quite a few definitions in the study of pack learning. H was defined as the hypothesis class. So this could be the set of linear classifiers or polynomial classifiers or neural networks and so on. We let x1, x2 up to xn be points in the Euclidean space. Okay. For any h in our hypothesis class, so for any specific classifier, h was a mapping from Rd to -1 and +1. So this was a classifier. So the classifier would either map to -1 or to +1. Okay. And h of x1, h of x2, if we evaluate the hypothesis on the endpoints, this is a vector from -1, +1 to the n. So this is, anybody knows what the name is for this vector? We discussed this last lecture. What's the name of a vector like this? So we have H is one hypothesis, which takes an input data vector and maps it to -1 and +1. It's the dichotomy vector, exactly. Okay. Now, capital H of x1 to xn is the dichotomy set. It is the collection of all dichotomy vectors in the hypothesis generated by the hypothesis class H. So this is the collection of vectors of the form h of x1 to h of xn for each h in the hypothesis class capital H. Okay. This is known as the dichotomy set. Then we define the growth function mh of n. This is the maximum value, the hypothesis, the maximum number of elements that can be in the hypothesis or the dichotomy set over all location of the points x1 to xn. We saw that for different values of x1 to xn, for different values of x1 to xn, we could have different size of dichotomy sets. For example, if we had like linear classifiers in 2 dimensions and the 3 points were collinear, we could only generate 6 dichotomies. If they were not collinear, we could generate all 8 dichotomies and so on. So the location of x1 to xn matters when we consider the size of the dichotomy set. And in the growth function, we look at the most optimistic placement of points. What is the placement of points that generates the maximum number of dichotomy vectors from H? Okay, that's the growth function. It's a function of the number of points only. It's not a function of x1 to xn because we optimize over it. And then we define the VC dimension, the Vapnik-Sherwood-Enkes dimension. It says that if mh of n equals 2 to the n and mh of n plus 1 is strictly less than 2 to the n plus 1, then the VC dimension equals n. The VC dimension is basically the maximum number of points for which the growth function equals 2 to the n. We call this shattering. We say H shatters n points if the size of the dichotomy set Hx is as large as possible, meaning it is 2 to the n. So the VC dimension simply is the maximum number of points that can be shattered by our hypothesis class. We discussed this last lecture. There is also something related called the breakpoint. We say that K is a breakpoint if no set of K points can be shattered by H. I didn't explicitly say it in our last lecture, but let me just write it down. So this is all review from last lecture. One additional definition is a breakpoint. K is a breakpoint of the hypothesis class H if MH of K is less than 2 to the K. So any K above the VC dimension will be a breakpoint, and any K less than or equal to VC dimension will not be a breakpoint. That's all it is. So any questions from last lecture, from all the definitions we did? In assignment 1, you will get a lot of rigorous sort of practice on these definitions. Have a lot of interesting questions. We evaluate the VC dimension for various hypothesis class to give properties, like if you take union of hypothesis class, what is the VC dimension? If you take intersection, what is the VC dimension? So a lot of interesting twists on this definition, which will be sort of intellectually interesting. I should mention there is a tutorial, like TA office hours for this course. Do you guys see the announcement? Okay, it's Mondays afternoon. So please try to make full use of it, because we probably will need it when doing the assignment. Don't leave anything to the last minute. It's going to be very hard. And so what is happening is I have given you the first set of problems in the assignment. I'll give second set of problems probably next week, or maybe a few days after next lecture. And then all of it will be due in the first week of February. I think Feb 4th. I will make everything due. So you'll have enough time, but start early, because you will get another set of questions. This is not it. So any questions about the logistics? Okay, so we'll start proving some properties of the growth function. We had this theorem last lecture, and we'll prove it in two parts. So part 1 is the following. If the VC dimension is finite, then MH of n is less than the summation of K going from 0 to dVC of H n choose K. And this is less than or equal to n dVC of H plus 1. This is the first thing we will prove, that the growth function, although it can be as large as 2 to the n in general, does not increase that fast. It only increases polynomially in the number of input points. It only increases as n to the dVC. So it's a polynomial function of n. The dVC is the VC dimension. The VC dimension is 10. The scaling is n to the 10. Okay. So this is the first major result that we will prove. And then we will use this to get a bound on the generalization error. So start with this. So this is, again, you can read the proof in the Learning from Data textbook. I will do the proof here, but as an additional reference, you can see chapter 2 of this text for the full proof. So define the following. We define a function b of nk. This denotes the maximum number of dichotomy vectors that can be generated under a combinatorial constraint that no k points have been shattered. Okay, so we want to look at a certain combinatorial quantity. We want to be able to enumerate all vectors of length n, where each coordinate can be plus or minus 1, such that if you look at any k coordinates, you cannot have all 2 to the k vectors in there. You have to have less than 2 to the k vector. This is the constraint we have. In general, there are 2 to the n vectors, dichotomy vectors, but then if you look at any k columns, they will also have all 2 to the k possibilities. So we don't want to have that. We want to have, if you look at any set of k columns, you should have less than 2 to the k. It can be any number. It can be 2 to the k minus 1. That's fine, but not 2 to the k. Okay. Is this clear, the definition? Let me do an example to clarify this further. So here we are not directly associating ourselves with the hypothesis class and the VC dimension yet. Okay, we are just defining an object. We are saying B and K is a number. And this number gives me the maximum number of dichotomy vectors of length n that can be generated under a constraint that no k points are shattered. So the dichotomy vectors, I should say here, this is of length n. So if I have, say, x1, x2, up to x, this is a dichotomy vector, then each of these coordinates is either minus 1 or plus 1. I can either have minus 1 here or plus 1, minus 1 or plus 1. And if I look at any collection of k coordinates, then in this set of dichotomy vectors that I generate, I should not have all 2 to the k options. Less than that is fine, but not all 2 to the k. So let's do a small example to clarify this. Say n is 3 and k is 2. So I have to consider dichotomy vectors of length 3 where no 2 coordinates are shattered. And let's just pretend that these are generated by a hypothesis class evaluated at points x1, x2, x3. Okay, and so I have a hypothesis class, and as I sweep through the different hypotheses, I generate different dichotomy vectors. Now I'm allowed to have all possible vectors of length 3, but no 2 points are shattered. So I cannot have all 4 combinations if I look at x1, x2, or x2, x3, and so on. So I may be allowed to have plus here, and plus here. Or I may be allowed to have plus, say this is what I have generated so far. So far everything is good. I just have 3 possibilities. So if I look at any set of 2 coordinates, I'm not shattering them because there are only 3 vectors. Let me add one. Can someone give me one more vector I can add so that the constraints are satisfied? I do not shatter any 2 coordinates. Okay, so I'll give you 2 options. One was minus, plus, plus. And let's consider another one, which is minus, minus, and plus. So is the first one feasible? Is this okay? Is it, if I take the first two coordinates, am I shattering them? No, that there is a plus plus, plus minus, minus plus. So let's not worry about this one right now. I just added it as a candidate. Just the first four, okay? So I can add this because these 2 points are okay. What about these two? I have plus plus, plus minus, minus plus, and plus plus, that's okay. There are only 3 vectors. And here I'm okay as well. Plus plus, plus minus, minus plus. So this is okay. Now what if instead of this I had added the last row? So instead of adding the fourth one, I added the last one. Will it work? No, because if you look at these two coordinates, I have plus plus, plus minus, minus plus, and minus minus. So this is not okay to add. So we'll remove that. This one was okay. So now I have 4, right? Can I add more than, can someone think of another one we could add? Actually, it turns out no matter how hard you think, you will not be able to add any more than this. Turns out you can at most add 4. So we'll later, as a result of this theorem, it turns out that B and K is less than summation of K. We'll show later that this is less than 4 no matter what you do. So this is the best you can do. So what this is showing is that if you have a combinatorial constraint like this, it puts a severe restriction on how many vectors you are able to add. And this is sort of a very important property. This is what we will build upon in our proof. That if you are allowed to enumerate all binary vectors, but you put a combinatorial constraint that no k coordinates can be fully shattered, the number of vectors you add is generally very small. And in fact, it will be small. It will be upper bounded by something like summation of j equals 0 to k minus 1 and choose j. This will be a bound on it, this is what we will show. In this example, this reduces to 3 choose 0 because n is 3, k is 2. If I look at this upper bound, it is 3 choose 0 plus 3 choose 1, which is 4. So as a result of that, no matter how you start with, what combinations you start with, how you proceed, you will never be able to have more than 4 dichotomy vectors in this particular example. Okay? So this is what we are going to prove. So is the definition of B and K clear? What B n comma K is? Now suppose H is a hypothesis class with K as the breakpoint. Suppose K is a breakpoint for the hypothesis class H. How is MH of n related to B and K? Can you even see the relationship between these two quantities? MH of n is the growth function of the hypothesis class H. It is the maximum number of dichotomy vectors of length n we can generate. However, H is required to have K as a breakpoint, meaning that if you take the growth function at k is at most 2 to the k. It cannot be equal to 2 to the k. It's strictly less than 2 to the k. Or any set of k coordinates cannot be shattered. So how is MH of n related to B n comma k? B and k is the maximum number of dichotomy vectors of length n you can ever hope to get under the constraint that no k points are shattered. And h of n is the maximum number of dichotomy vectors that can be generated by the hypothesis class H when k is a breakpoint. It's less than, that's it, that's all I was looking for. It has to be less than or equal to, right? This is the most you can ever hope for and this is basically what you're looking for. This is the what you want to bound. And so if we do show that this is less than, if we do prove this, that this is less than j equals 0 to k minus 1 and choose j, we are basically done, because we know that dv, like if I set k to be dvc plus 1, it's a breakpoint. dvc is the maximum number of points that can be shattered. Since k equals dvc plus 1 is a breakpoint, this will complete our proof. Because then I can substitute k to be dvc plus 1, I get j equals 0 to dvc of n choose j, which is what we claimed in our original statement here. So all we have to prove now is this property, that this function b and k is less than summation of j equals 0 to k minus 1 and choose j. If we prove this, then it will complete the proof. So the next part of our lecture will be to prove this. It's a little bit of a counting argument, and it's combinatorial in nature, which is expected from all the definitions. We'll go and do that. Okay, so let's start with some boundary cases. Can anyone tell me what b of n k equals 1 is for all n greater than or equal to 1? What is the maximum value you can get for b of n when k is 1? So you're not allowed to shatter even one coordinate. If you look at the first coordinate, among all the vectors that can be generated, the first coordinate has to be either plus or minus, but it cannot be both. It's 1. That's right? Like, the only value you can take, this is the number of vectors you can generate is 1. Because say you fix any vector, say if you fix plus 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 like this, then to get another vector, you have to change at least one coordinate. If you want to add a second vector, you have to at least change one of the coordinates. But that is shattering that particular coordinate. Now you have, like, then you cannot have k equals 1. Because k equals 1 means no coordinate can be shattered. You cannot have two combinations at any one point. So this is clear. What about b of n equals 1 and k equals 2? What is that going to be? Or let's just do general k for all k greater than or equal to 2. If I only look at dichotomy vectors of length 1 and k has no constraint, k can be greater than or equal to 2, then I'm only looking at dichotomy vectors of length 1. So as such, I can only have plus or minus as my candidates, and they're both feasible. So this is equal to 2. Okay. So these two are the base cases. Now we will do the recursion. And for recursion, just to intuitively, it is always good to associate this with a dichotomy set. So what we will do is, suppose that b and k represent the dichotomy vectors S. So S is the set of dichotomy vectors that are generated by some hypothesis set H over points x1, x2 up to xn. So just for our own convenience and to break the argument, what we will assume is the following. We have the dichotomy vector, which is the collection of vectors of length n under this constraint that no k coordinates are shattered. What we will assume is that it is generated, there is some hypothesis class that is generating it, some hypothesis class H, and it is obtained by evaluating it over x1 to xn. We can trivially define such hypothesis class. This is without loss of generality. It will just make our discussion easier. Okay. So this will allow us to draw a picture, and just we will see how the argument follows. But there is nothing special. There is no assumption, no loss of generality in this. And what is important is that this set will be called S. So S is the collection of the vectors that we are interested in. So just so that we understand this particular statement, we can view it via this table. So we have x1, x2 up to xn. These are the points where the vectors are generated. S is the collection of all the points, right? This is the set of all the vectors that I am enumerating. In order to enumerate S, I will basically have vectors like this: +1, +1, let me write x3 actually, +1, this is +1, so this is one dichotomy vector of all ones. Another one could be +1, -1, -1, +1, -1, and so on. I'm just writing some arbitrary vectors like this. Now, this set of vectors have been selected with one special property. If you look at the last coordinate, if there is a +1, you will not have the same vector here with -1. Either you have +1 here or -1. So this vector of length n-1 will not get repeated with a -1 here. So there is no copy of this vector here of all +1s with a -1. So this is one set of vectors that I have in the set S. So these are vectors where if you have a +1 in the last or -1 in the last position, you will not have the flipped version of it with the same prefix to it. So this is one set, S1. So this is a set of vectors which says that if +1 appears at xn, then -1 will not appear, and vice versa. Meaning that if -1 appears here, you will not have a copy of this prefix with +1. So let me write it down. S1 is a subset of S, or actually S1 here is the dichotomies over x1 to xn-1 which appear only once in S with either +1 or -1 at xn, but not both. Okay, so S1 is dichotomies of length n-1. You're only looking at prefix, and it is those vectors such that if you add +1, you will see that vector in S, or if you add -1, you will see that vector in the original set S. But you cannot have both the vectors simultaneously appear. That's what S1 is. For S2, we will have the vectors where the prefixes where both +1 and -1 appear. So for S2, we will have, say, +1, -1, and like this. And +1 will appear, and another copy of this, +1, -1. So this is this is in a sense a duplicate. This vector is a duplicate of this. But at the last coordinate, both +1 and -1 simultaneously appear in this. Similarly, there could be another one, -1, -1, and then another copy of this with a -1. So these are duplicates. Okay. And S2 will be the collection of all such vectors at the first n-1 positions. Okay. S2 is the collection of all dichotomy vectors that if +1 appears at xn, then -1 also appears. So S2 is the dichotomies over x1 to xn-1 such that if +1 appears at xn, then -1 also appears. So these are the dichotomy vectors. These are the prefixes of the original dichotomy vectors that appear twice. One with +1 appended at the last position, one with -1 appended at the last position. Okay. Now suppose the size of S1 equals alpha and the size of S2 equals beta. Suppose we say that these are the sizes of S1. So the vectors here and the vectors here. Okay, so question 1, is there any intersection between S1 and S2? Can there be any vector common between S1 and S2? Can you have a vector that is in S2 and also in S1? Yeah, I see some people nodding no. Anyone explain why? Why is it that if we have a vector here, it cannot appear in, yeah?
So if it's in S2, that means it exists with a 1+1 in the last column and a -1 in the last column, which implies that it is not.
Exactly, that's it. So that's just excellent. That's exactly the argument. So you cannot have the same vector in S1 and S2 because if it happened in S2, it has to occur in S with both +1 and -1 in the last position. Okay? So whereas here, if it happens in S1, it can only happen with either +1 or -1 in the last position. It cannot happen with both values. Hence, by definition, S1 and S2 are disjoint. Is this clear? Okay. So can anyone give me the size of S, the original set in terms of these quantities, alpha and beta, the size of S1 and the size of S2? Can anyone give me what the size of the original set will be in terms of alpha and beta? Someone other than you, if you understand. So if I have, say, alpha vectors here, these all happen, so these are all dichotomy vectors of length n-1. And then to get them to S, I have to either append +1 or -1, depending on the dichotomy vector. Okay, so they all appear once. For S2, If I have any vector in S2, it appears with +1, and the same vector is repeated with -1. Okay? So each of this vector will appear twice. If I have any element in S2, it will appear in this row, and then it will also appear, a duplicate of it will appear with -1. So when I'm going to count over all sort of elements in S, the original vector, I have to count each element in S once and have to count each element in S2 twice. So can anyone? I think I almost given away the answer. So I want you to be confident and answer. This is the easier proof than the next one we will do, by the way. The second half of the theorem is much harder than the first half.
Guessing it's just alpha plus 2 beta.
That's it. Alpha. I know most of you knew it, but I wanted to make sure somebody is confident and replies. Okay? This is what it will be in terms of alpha and beta. So basically we are counting each element here once. There are alpha of them and they all appear in S once. There are beta of them and they appear twice. So that's why I says alpha plus 2 beta. So this is what we want to upper bound. Any questions? This is a good time to ask. Yeah?
Explain what is exactly S, because I see that, so if there's S1, S2, and there's overlap between S1 and S2. So S1 and S2 are to destroying the set, right? But the elements in S1 and S2, there's some like half of the elements in S2 is the same as S1, because you add like the +1 to the -1 dichotomy sequences.
I'm not entirely sure. Maybe I can clarify the definition of S1, S2, and S. So S is the collection of all binary vectors of length n that are generated by this hypothesis class. So it's basically, this is one element, this is another element, this is all the entire vector of length n. Okay? So the total size of S is this entire, all total number of rows we have here. Okay? For S1 and S2, when we define, we ignore sort of the last coordinate. We do not look at, when we are defining S1 and S2, we are only looking at the left. We are only looking at prefixes of these vectors.
But when we are looking at the prefixes, are the prefixes for S1, S2 the same?
The prefixes for S1 and S2, what do you mean by that? So S1 is a collection of vectors of length n minus 1. S2 is a collection of vectors of length n minus 1. And the vectors here are prefixes of the vectors in the set S. So just to clarify the terminology. Okay, now can you ask your question?
Yeah, so for example, so if the -1 prefixes shatters the space, so there may be due to the n-1 total sequences.
No, they won't shatter the space in general. Let's do it offline. Yeah? Yes. So dichotomy S is the collection of dichotomy vectors of length n. But just to sort of bound the size of S, we are going to have a recursive argument. So we're going to look at dichotomy vectors of length n minus 1. By induction, assume that they have certain size and use them to bound the size of this overall set S. Now, S1 and S2 are sort of selected, so they have different structures, right? S1 will be all vectors such that if you add either +1 or -1 in the last position, you get an element in S, but not both. S2 will be the collection of all vectors such that if you add +1 and -1, both of them will be in the original set S. That's the only sort of, this is without loss of generality again. You can always partition S in this form. Perhaps the size of S2 is 0 or the size of S1 is 0, but that's okay with us. This is, you can always do this sort of definition of splitting S into S1 and S2. Any other questions? Okay. So now consider the dichotomy vectors of length n minus 1 in S1 union S2. What we'll do next is we'll consider the dichotomy vectors of length n minus 1 in S1 union S2. So what we are doing in this table is, this is S1. This is the collection of dichotomy vectors here in S1, right? This is the collection of dichotomy vectors in S2. And then these are duplicated here when we enumerate S. So we are looking at this set here. So this is S1 and this is S2. So we are looking at this set, this collection of vectors of length n minus 1. What is the size of S1 union S2? Alpha plus beta, right? So let's write that down. Okay. Now the claim is that if you look at this collection of vectors and you look at any k coordinates here, they cannot be shattered. If you look at any k coordinates in this set of vectors, you cannot have all 2 to the k combinations. Can anyone see why? Why is it that if I look at this collection of vectors and look at any k coordinates, I won't be able to see all 2 to the k combinations? So if I take k to be 2, for example, if k was 2 in my B and k, and if I look at x1, x2, then I should not have all 4 combinations. Why is that the case? Let me write it down. Claim that no k positions or coordinates in S1 union S2 can be shattered. That is, you have all 2 to the k possibilities. Why is that? Can anyone give a proof? Like a one-line argument? Complicated? Someone from this side? Is it clear what we are saying? Any questions what we are saying here? The statement clear? So you have vectors of length n in n minus 1 in S1 union S2. And I'm claiming that if I look at any k coordinates, then I won't be able to see all 2 to the k possibilities in this collection. So imagine that if I look at S1 union S2, I have n minus 1 positions, so I may get something like this, and so on. And what I'm saying is that if I look at any k positions, no matter how I select k, if I look at any k coordinates and don't look at the other ones, then I won't be able to see all 2 to the k labels, like all 2 to the k vectors. this clear what I'm claiming? Any questions about the statement? Because if you understand the statement, the proof is very easy. I'm not going to continue unless someone answers. That's the deal. You just will learn very little in the end if you don't answer. So what is it that you don't like, that you don't want to speak up? You don't understand the statement of what I'm claiming, or you don't understand how to prove it?
I can't see the proof. I don't.
Okay, good. Yeah. Okay. Sure. So if this was, if you could find k columns such that you enumerate all possible vectors, because this matrix is like a submatrix of the S matrix, this would imply that S.
That's it. That's it. It directly follows by contradiction, because I could add one more row. I know that each of this is a prefix in the original set of dichotomy vectors. I could either have +1, something like this. Okay. Now suppose that I could find all 2 to the k possibilities here. Then each of this vector belongs to the original set S. Right? So then this, what I'm saying is, in the original set S, this k collection of points is also shattered. So if I had this original collection of vectors and I again focused on the k coordinates, I would see all 2 to the k combinations here as well. So this is a contradiction, because we said that in the definition of B and K, no collection of k points is shattered. So if proof by contradiction, if k points are shattered in S1 union S2, these k points are also shattered in the original set S, because the original set S has these vectors as a prefix. So they are exactly as they are. We just append either +1 or -1. Doesn't matter. You just look at these k points. These have all 2 to the k combinations. They are shattered in this set, so they are shattered in S as well. But the definition of B and K says that no collection of k points can be shattered. So contradicts is one student who's very far ahead. I think the rest have to now catch up. Play very close attention. I think a few students here are good. But is this clear? Yes, no questions? Anything that needs to be clarified? Do so now. And so what does this say? How can you bound? What kind of bound can you have on alpha and alpha plus beta? We know that alpha plus beta is the size of S1 union S2. S1 union S2 has a property that it consists of dichotomy vectors of length n-1 such that no k points are shattered. As a result of this, we can immediately say this is less than b of n minus 1 comma k. What we are saying here is that this is the maximum number of vectors of length n minus 1 that can exist such that no k points are shattered. S1 plus union S2 is one instantiation of vectors of length n minus 1 where no k points are shattered. As a result, this follows by definition. Okay. All right. I will do one more claim. There is a second claim. Now let's just consider the set S2. So the claim is that no k minus 1, no collection of k minus 1 points is shattered in S2. This is the claim. If you look at any k minus 1 positions, they cannot be shattered in S2. So remember, S2 was a collection of vectors of length n minus 1. Okay, it could be maybe plus 1 like this, something like this, such that if you had a vector like this, you would see a duplicate of this. So you will see a duplicate vector once with plus 1 and once with minus 1. So each vector here will appear in S with plus 1 and later with minus 1. This is the definition of vectors in S2. So S2 consists of vectors of length n minus 1. Now we are claiming that, so this is S2 here, the vectors of length n minus 1. Okay. What we are claiming is if I look at any k positions, so maybe the first k positions, then I cannot have all 2 to the k vectors in this set at these positions in S2. Why is that? Or, sorry, k minus 1, not k. If I look at any k minus 1 positions, then I cannot have all 2 to the k minus 1 possibilities. So, who wants to explain why this is the case? Yeah?
Can I just say my point of view? So actually, we were just duplicating like from very beginning. So I'm asking, for example, the first one is plus, and you add plus and minus. So this does not shatter the space, and you duplicate those every time, and I think you always will not like shatter the space because at the first one there's no minus at the first one.
So I'm not entirely sure. So you're saying that suppose there is a collection of k minus 1 points such that all 2 to the k minus 1 vectors are observed. Let's say, for sake of argument, that is the case. Why will that lead to a contradiction in our definition of S? So what we want to say is that we cannot have in S2 any k minus 1 positions where all 2 to the k minus 1 vectors are seen in S2. Because if that happens, then we will lead to some contradiction in the definition of S. Yeah?
Because, like, suppose you have like vectors where 2 to the k minus 1 points are shattered. If you look at the last component, by adding the last component, basically you're shattering that component as well. So basically you have 2 to the k components that are shattered in that bigger set.
That's the concept. Perfect. Beautiful. So the idea is that if you had this k minus 1 positions, you could add plus 1 and the same vector appears with minus 1. So now these k minus 1 positions along with the last coordinate is going to be k points that are shattered in the original set S. And this is a contradiction because no k points can be shattered in S. Is this clear? So let me write it down. So I'll write it on the next page, just so that we have everything on one page. Suppose these points are shattered in S2. Then, since x1 to xk minus 1 and xn equals plus 1, as well as x1 to xk minus 1 and xn equals minus 1, both, this is sort of a not the best notation to have. So let me rewrite this. Then since each dichotomy vector appears in S with both plus 1 and minus 1 at xn, it follows that x1 to xk minus 1 and xn is shattered in S. So for all 2 to the k minus 1 possibilities at x1 to xk minus 1, you will have both plus 1 and minus 1 at the last position. So you will have 2 times 2 to the k minus 1, which is 2 to the k possibilities, which means you are shattering the set S at these k positions. This is a contradiction. Okay. As a result of this, what we have said is the size of S2, which is beta, should be less than b of n minus 1, k minus 1. Since no k minus 1 points can be shattered in S2, S2 has dichotomy vectors of length n minus 1, it follows that beta is less than b of n minus 1, k minus 1. So what we have shown so far, the size of S is alpha plus 2 beta. We showed that. We showed that alpha plus beta is less than b of n minus 1 comma k. This was claim 1. And then we showed that beta is less than b of n minus 1, k minus 1. This was claim 2. This is all we have shown so far. So now to get the size of S, it's alpha plus 2 beta, which is the sum of the two quantities on the left-hand side, which is upper bounded by the sum of the two quantities on the right-hand side. and that will be our recursion. Now, byte S was defined to be the largest collection of vectors of length n where no k points are shattered. And so by construction of in our statement, S is the largest collection of vectors of length n where no k points are shattered. The size of S by definition is B of n comma k. This is how we started off. Thus, what we have shown is that B of nk is less than B of n minus 1, k minus 1 plus B of n minus 1 k. This is the recursion that we have shown so far. Now we can use this to numerically evaluate B of nk. We have the base cases. Okay. So this is n, this is k. K is 1, 2, 3. N is 1, 2, 3, 4, 5. Okay. First, like when k is 1, P of n comma 1 is always 1. This was one of the base cases we had. If k is 1, P of nk is all 1s. And if n is 1 and k is greater than or equal to 2, B of nk is 2. For the remaining ones, if we want to fill up this cell, we will only give an upper bound. We'll say that this cell is less than B of, here n is 2 and k is 2. So B of 2, 2 is less than B of 1, 1 plus B of 1, 2. So we add these two. If you want to look at this cell, then it is less than B of n minus 1, k minus 1 plus B of n minus 1, k. So it's the sum of these two. Okay? And likewise, here it's the sum of these two. And you can continue. This one here is the sum of these two, less than the sum of these two. So on. So this is how you can fill up the table recursively by just upper. So all of these are upper bounds. They're not exact necessarily, but this is how you can recursively compute. And there is a lemma. You can also use this recursion and properties of the n choose k function to complete the proof. Once you have this, there is a lemma called Sauer's lemma, which says that B of nk is less than the summation of j going from 0 to k and choose j. I think j, whatever we had, 0 to k minus 1, the statement of the proof. So the final result follows from by just expanding this binomial summation, and you end up with this. So this is the first part of the proof. Like after the break, we'll take a break now, and then we will show that we will use this result to compute the generalization error. So this is the second half of the theorem, which will now, in all of this is combinatorics, the second half will be all probability. So Hovding's inequality, very carefully applied and so on. So we'll take a 10-minute break. You can ask me any questions and then we can continue.